back to the code space. In this video, we are going to learn the next data structure, which is very important while solving the problems. It is a very generic data structure which can be useful in any type of range queries or any type of query. First of all, let us introduce what is a segment tree. Segment tree is a range querying data structure in which we can make updations, range updations. The specialty about this tree compared to other data structures like prefix or a Fenwick tree, this segment tree can do range updates. So another specialty about this tree is for a operation to be queried using on an array using Fenwick tree or a prefix can only be possible if the operation is invertible, as I have explained in the videos of prefix and as well as in the Fenwick tree, that if you want to query a range for prefix or Fenwick tree, operation that you are going to perform, like for example in the case of sum, if you need any range sum, the operation is sum, and if you need any maximum element in the given range, then the operation is said to be the maximum. If that operation is not invertible, then we can't get the range query from L to R. But for segment tree, we can still achieve, but for segment tree, there is no necessity of operation to be invertible. This is the main point which makes the fetch segment tree applicable for any range query. I hope you have cleared with that point. Now let's consider a array. Let's see how the segment tree is stores the values. Let us consider an array in which we have to perform, like we have to construct a segment tree to perform some range queries, maximum range queries from L to R, any range. Maximum in L to R. So the segment tree is constructed in such a way that the leaf nodes of that tree will be as same as the values stored in the array. And then let us place the leaf nodes. 5 goes here, and then 12 goes here, 4 goes here, and 32 goes here, and 34. We have successfully updated the leaf node values to the given values. So the parent node of these leaves is going to be the maximum of those leaf nodes. Like here we are, the operation is maximum, so we are going to store here the maximum value of 2 comma 5, that is nothing but 5. So we'll store a value 5 here. And similarly, if we apply the maximum operation on 12 and 4, we'll get 12, which is going to be stored here. And if we store the maximum of 32 and 34, it is going to be 34. And if we take the maximum of 21 and 18, it is going to be 21. So again, we'll repeat the same process until we reach the node root node. So the maximum of these two is going to be 12, and the maximum of 34 and 21 is clearly 34, which is going to be placed here. And the maximum of 34 and 12 is going to be the 34, which is going to be placed on the root node. So what is the use of maintaining these maximums extra? So the use is, if we need, see, let's see how the time complexity is being decreased by this segment tree. If we need from 0 to 7 index, maximum of from 0 to 7, we can simply go to the read root node and take the value present at that. It means we can achieve the maximum from 0 to 7 in order of 1. Maximum from 0 to 7 in order of 1. This is the main application of this segment tree. So let's consider a general range from L to R. Let's take an example from the range 3 to 6. Let us compute the maximum for this. So when you query the maximum from 3 to 6, see here each node is assigned with a small range, which simply implies that the number stored at that node is the maximum of that range. For example, for the root node, it is going to be from 0 to 7. It stores maximum from 0 to 7, all nodes. And for this node, left child of this root node, the range is divided into two halves, and one half is assigned to the left part and the other half is simply assigned to the right part. So simply we'll do 7 by 2, which is going to be 3. So we'll store the maximum from 0 to 3 at the node left child of the root node. And similarly, we'll store the maximum from fourth index to the last index 7 on the right node. And again, we'll divide this parent range into two halves and assign the left half to the left child and the right half to the right child. So here we'll have the range from 0 to 1 and 1 to 3 to the right part. And similarly, we'll have the range from 0 to 0, 0 to 1. So in the same way, each node will be assigned to a unique range which will return the maximum value in that range. So once we assign each node, we'll query from 3 to 6. First, we'll reach to the root node. Here, we'll come across three conditions. One is complete map, complete. When we reach to a particular node, there are three possibilities between the query range and the range of that node. There can be the complete overlap, or partial overlap or no overlap. Let us see the case like if the node ranges are completely overlapping with the query range, and partial overlap if the node ranges are partially overlapping with the query range. Here we can simply see that once we query the range from 3 to 6, we'll first reach to the root node. So the node ranges will be from 0 to 7, and the query ranges are from 3 to 6, which means that here is the case of partial overlap. No overlap if the node ranges are and if the node ranges and the query ranges has no overlapping range, then in that case it is known as no overlap. This, like, let us see the how the query 3 to 6 will be evaluated. First we'll reach to the node root node, and there occurs a partial overlap. If it is the case of partial overlap, then we'll recursively call both childs of that node. For example, in this case, we'll reach to the left child and as well as right child. And once we reach to the, let us give some numbering to these nodes so that we can identify each of them. This is root 1 and node 1, node 2, node 3, node 4, node 5, node 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. The first call reaches to the node 1, and encounter a partial overlap, and then reaches to the node 2. Here the range of node 2 is from 0 to 4, which simply again a partial overlap, which calls the left child of that node, node 4, whose range is from 0 to 2. Let's see. Which is no overlap case. In no overlap case, we don't further go to its child, and we'll backtrack to the node 2, node two's right child, which is node 5. And this is the case of case of partial overlap again. Node 5 is also a partial overlap, which simply calls its child, that is node 10, which is a case of no overlap. So we'll not go further and we'll go to the right child of this node 5, which is node 11. This is a complete overlap, so it will return the maximum value of 12. Like the maximum value of node 11 is 4, so it will returns 4 and backtrack to the node 5, and the children's of node 5 is completed, so it will again backtrack to the node 12 with value returning. This value 4 is returned to the node 2 until it reaches the node 2, and again the node 3 in the same way it will give the maximum, like it will encounter a partial overlap which will be divided into 2, and 2 to 5 is is a complete overlap, and the right child, which is from 6 to 7, is a partial overlap which will return the maximum value from the range 6 to 6 by from its left child. So it will return, overall it will give the maximum value of 34 and 21. So will at the last it will backtrack to the node 1 and return the maximum value of 4 and 34, which is going to be the 34. Final answer is 34. So in this way, a query is being executed in a segment tree. So I hope you have understand and got a clear idea on the query operation of a segment tree. In the next video, we're going to see the implementation of the query on segment tree. Thank you for watching.